Hello everyone, welcome to our UCLA IDRE and OARC workshops. My name is Xiyang Hu. Today our topic would be a Python library named Scikit-Learn. We will learn what is Scikit-Learn and how to use it. My talks about Scikit-Learn can be divided into two parts. The first, we will focus on the basics. So we will make a fairly fundamental introduction and high-level overview of the whole libraries. So this will be presented for today. And in the 2 days later, my second talk will focus on some advanced topics. Specifically, we will talk about the high-performance machine learning using Scikit-Learn. So we will consider the two basic major questions. One is how to make the computation faster, and second would be how to process the large dataset that it cannot fit into the memory. Because Scikit-Learn is a huge library, before we formally started our talk, I would like to spend a couple of minutes to see what can and cannot be expected in the whole theory. The first is Scikit-Learn is for machine learning, and we will introduce our libraries interfaces along with the typical machine learning workflow. So we will review that kind of workflow, of course, but we cannot expect to have some detailed discussion about the various machine learning models or algorithms. So that's out of our scope. And also, Scikit-Learn, they have hundreds of features, thousands of interfaces, functions, and components. So we will not discuss the very details for some APIs, parameters, default values, or possible options. Instead, we will discuss, I will try to give you a bigger picture to see, okay, what's the design, what's the logic for the Scikit-Learn's interface designs. And also, along with my talk with the slides, I actually provide a lot of handy examples as demos. And ideally, I would expect that anyone who are really interested in the Scikit-Learn, you may just spend a little bit more time after the class to study by yourself for the demos, and we don't have the time to make the explanation line by line for every demo code. And the same thing happened for our advanced topics for the Scikit-Learn. And because this will discuss a lot of high level, high performance machine learning topics, and the concerns, considerations, and the approaches, people how to solve that. So we will give you a very high level introduction and overview. And you may not expect to see some detailed implementations or mechanism for that kind of topic. Now let's get started to learn the Scikit-Learn basics. The first question to answer is, what is Scikit-Learn? Scikit-Learn is a Python-based library for machine learning. So it provides tons of simple and efficient tools for predictive data analysis. It is a library built upon the other Python libraries. Specifically, it used the NumPy for array vectorizations, used the pandas data frames, and it used the SciPy and many more other libraries for the scientific calculations. And also, it uses matplotlib and plotly for plotting. So the project was originally started in 2007 as a Google Summer of Code project. The leader at that time named, David Kernapol. So the Scikit-Learn's name itself stems from the notation that it is a Scikit, meaning the SciPy toolkit. It serves as the third-party extension to the SciPy. And after that, it became so popular and it publicly released in 2010 by the leadership of the project at that time. Now it's currently is maintained by a lot of volunteers, and it is formed a very thriving international community. The last time, a couple of months ago, I checked with the GitHub. I think there's already over 2,000 contributors for the Scikit-Learn. To install and to load Scikit-Learn is pretty simple. Because it is a Python library, you can use the pip install or conda install, pretty straightforward. For here, I'm just giving you an example that if you would like to install the Scikit-Learn on your local desktop or laptop, and I actually specifically added the -c, that's the conda channel using the Intel version 1. It's this version of Scikit-Learn provide an alternative solvers for some common estimators. So specifically, those solvers come from the Intel DALC++ library, and it's actually optimized for multi-core Intel CPU. So if your laptop or desktop equipped with Intel CPU, I strongly recommend that you use this version of Scikit-Learn for your personal use. So we will discuss a lot of details about that kind of optimization version of the Scikit-Learn in my second talk for the high-performance machine learning using Scikit-Learn. And for UCLA users on Hopin-2 high-performance cluster, you can simply use the module load Anaconda 3. So we actually have a conda environment named as Scikit-Learn. So you can, after you load your model for the Anaconda 3, so you can conda activate that Scikit-Learn, and then you can start using that in your interactive session or in your batch job. But I would say that because the Hopin-2 actually have the multiple type of CPUs in the cluster, in this version that I installed a couple of months ago, so we don't support any Intel optimized like accelerations on that. So we actually not install the Scikit-Learn using the -c Intel version. So that's a keep in mind. In our talk, today's talk, we were not using those two methods. We actually using the Google Colab. All the demos are actually in the form of a Python notebook, and it can be directly loaded in the Google Colab. So everybody, as long as you have a Google account and you have a web browser, and you can start it using that right away. I believe that this would be the easiest way to showing the demo for everyone. A big reason for the Scikit-Learn becomes so popular in the machine learning community is that the library is designed for easy to use productions. Easy to use meaning the structure and the logics in the library are very simple. And for productions, meaning the quality of code itself is very good. Specifically, you can get a very good performance even if you don't use any fancy techniques. You just use the plain vanilla version of Scikit-Learn, and then you can get a high performance linear algebra and array operations with the SciPy integrated in the Scikit-Learn library itself. And some core algorithms in estimators are even directly written in the Python to speed up the speed. And also the elegant itself are very elegant. So it may not be the first one to propose that kind of API, but then the API along that line becomes sort of de facto, and almost all the machine learning frameworks adopt the same approach. We know that Scikit-Learn is a big one, big library, but you can really see how easy it can be used by just a few lines of code that I showed in the slides here. This snippet of code I just copied from their documentation site. As a typical machine learning project, so all the code can be divided into three parts. The first is the data. So we collect the data and we ingress the data and then we sort it out into some format of the data. And then we started defining the models that we select, what kind of model that we use to analyze, to train the data. And then the third part would be to make the prediction. You can see that the data itself is just the NumPy, and of course Scikit-Learn will have its own just the big collection of the data part. So we will discuss in details in our later slides. But look at the modeling part. So to use Scikit-Learn to make the training, to make the modeling, to make the modeling for the project is pretty simple. So you just import the corresponding models and then you define the models as this. And then you call the model dot fit with your training data and with your labeling of the data. And then you can make the predictions by the model's name dot predict. And then you can predict the training data, and also you can predict the new data. So that's it. Almost no matter how complicated for your problem is, you just follow those 3 steps, and then in each of those steps, Scikit-Learn will provide a bunch of tools for you to finish that kind of 3 steps. One more thing I wanted added for the introduction to Scikit-Learn is its documentations. In my personal opinion, this might be the best Python library documentations that I've ever used. I started learning that just checking with documentations by myself. I found every piece of articles and the guidance and the examples are linked very logically in the documentations. So I would recommend everyone who wanted to learn the Scikit-Learn, go to their website, and you will find that you can quickly find information what you need. So that's pretty good. Technically, this page might be all you need to start for using Scikit-Learn. And in this lecture, I like to do something beyond that. What I will do is to provide a bigger picture for different components, features, and functions for the Scikit-Learn to you according to different steps of machine learning project workflow. This is the simplified workflow for a typical machine learning project. I would say that may be oversimplified version, but I think it would be enough for our illustration using for the Scikit-Learn. Every machine learning project was started by getting the data or collecting the data. After we got the data, we need to split the data. One part would be for the training, maybe 60% or 70% of the data for the training, and the rest 30 to 40% for the testing. The next is to explore the data. So we will know our data, to understand the data, and then to pre-processing the data, maybe to do with some feature extractions, that kind of thing, and feature selection for the data. Then the next step would be to selecting the data and selecting the corresponding loss functions, of course. And then we use the data, training data, to train the model and to evaluate the model. There's an iteration loops among the different models to evaluate the model. Okay, and then I didn't actually in practice. We will need to do another iteration loops to apply the different splitting schemes for the data, for the training and the testing data, to make us to select the best model with the highest evaluate performance scores. Whenever we got the model that performs best, then we can apply that kind of model for the new production data and then to produce our desired predictions. And Scikit-Learn in that sense is not quite a framework, but we better to consider that as the toolbox kit. So it provides a tons of tools that can apply in their every component along that kind of workflow. Let's get started with the first step, that is getting or acquiring or collecting the data. As we mentioned before, Scikit-Learn is built up upon the other Python libraries like NumPy or SciPy, so there's no surprise that they can get the input from any data format from the NumPy. For example, if your data don't have so many zeros, that we call the dense data, so they can in the format of IDRE in the NumPy, or in the series in the pandas, or in the data frames in the pandas. If your data have a lot of zeros, so that what we call the sparse data, then you can input the scipy.sparse in the data format of, they call it the COO coordinate format. That is no surprise for that. At the same time, Scikit-Learn come up with a lot of standard datasets for the users to learn and to test for their models. Some datasets are pretty small, that I call it toy datasets here. So those datasets are so small that they can come up within the Scikit-Learn packages. One of the good example for here is IRIS datasets. This is perhaps the best known database to be found in the pattern recognition literature. And the dataset contains only 3 classes of 50 instances each. So you can imagine that the data size is pretty small. You can simply type with sklearn.datasets.load underscore with the name that I listed here to get the data. Other standard datasets that provided from the Scikit-Learn what we call as real-world datasets. Those datasets are relatively large compared with the toy datasets, so the Scikit-Learn will not actually include the data itself in the package. They provided with the datasets.fetch underscore for the name of the datasets, and then to let you to download it whenever you need it. For example, in the California housing would be the datasets that we will use in our demo, and also we shown up in some third party of the OpenML, which is OpenML is a public repository for machine learning data and experiments. Our example would be to download the datasets of gene expressions in the MySprings. So you will see that it's very pretty handy for users to download the datasets like that. One more thing I wanted added for the data input and loader is that for all the loaders and the fetchers in the Scikit-Learn, they actually return a dictionary-like bunch object. So that's the default behavior. So what is a bunch object? It's a bunch object. It's just a dictionary that exposes its keys as attributes. So basically, you can call this. You can get the data by the index as well as the keys as well as the attributes. One more thing I wanted to add for the Scikit-Learn data input and loader is that for every loaders and the fetchers, the default behavior is that they will return a bunch object, Python bunch object. So what is Python object? It is just a dictionary that exposes its keys as attribute. So basically, you can get the value not only by the index, but also by the attributes like a b.b with this example here. In addition to providing some existing standard datasets, Scikit-Learn provided with some mechanism to generate some artificial data for the testing or for learning purposes to the users. And you can find like you may simply use sklearn.datasets.make underscore with blob classification, Gaussian quantiles, such and such moons, all different names so that they can define with different type of the data that you want to form. One of the good example that we will show in our demo is the blob thing. So the blob meaning for here in the Scikit-Learn meaning they will generate isotropic Gaussian blobs for the clustering problems. And I listed here for a couple of options that you can provide with that. For example, like you can give how many number of samples you want to generate, how many features or clustering you want to generate, and such and such. That's a very useful and very handy during our learning and testing for models for the utilities such and such. So we finished collecting our data. So whenever we got the raw data, what we needed, and the next task would be to split the data into the two groups. One is named the training dataset, and others is the testing dataset. Roughly speaking, splitting datasets meaning we will split the array or matrices into the random train and test subsets. So that's a pretty important step because it's a process related with the model evaluation and selection. We will need to evaluate the model with the fresh data for every time that hasn't been seen by the model before. So for here, you can see that our goal is to get an unbiased evaluation. Unbiased evaluation means that you cannot evaluate the predictive performance of a model with the same data. So that's pretty important. Actually, splitting the data is not a simple task because depending on different data sets, different splitting techniques have to be applied. And the most common one might be stratified splitting. It means that we will split the data according to its class labels. Well, in some cases, if your data were divided by the groups on top of the labels, you have to use some specific group splitting because stratified splitting cannot account for any groups. So Scikit-Learn provides us lots of group splitting methods. Some called like group k-fold, leave one, leave out, leave p groups out, such and such. So all you can check in the documents for the Scikit-Learn. Another type of the data is time series data. So meaning all the data are sequence related. So you cannot apply with some random permutation for those kind of data. So you have to apply with some specific splitting method. In Scikit-Learn, they call it a time series split. Also, Scikit-Learn provided with some customized splitting method that they call it as predefined, so that you can define your own splitting schemes. And of course, we don't have time to go over all those splitting methods. Instead, we will focus on stratified splitting. That's the common cases. And Scikit-Learn provided with a very handy function. They call it the train test split function. It is a wrapper around the shuffle split, and it only allows for the stratified splitting, no group splitting or time series splitting in this case. And it's as a base for the default cross-validation as well. Here, I use a pretty simple example to show how to use the train test split. You can notice that train test split is coming from the module, they call it sklearn.module_selection. We use the standard IDRE database to return the test and the data and the target by using the return_x_y, because if by default this option equals to false, meaning we just return a bunch object, but for the equals to true, meaning we want to return with the data and the target separately. So for the train and the test split, we simply just provide it with that kind of a data as x and y data and the target, and then we ask that is test size equal to 0.4, meaning we use 60% of data as the training and 40% as testing. And the random state would be we give the number so that we want to reproduce our training results. So that's as simple as that, because for every time you're running this one, they were actually randomly shuffling the data, and then you grab the different parts of the 40% or 60% of the data as a training or the testing. So that's our purpose. After splitting the training and testing data, we will come into the steps to process data, to modeling the data, to train the data, and to predict the data. So all those parts of the job will lead us to touch the core objects of the Scikit-Learn. In Scikit-Learn, there are four main core objects. In some contexts that people also call, there are four core estimators. Each of them provides distinctive methods. One of them, and the most important one, is called estimator. I know there is a little bit confusing because they use the estimator for all four core objects, but for here, they're actually using the estimator, meaning that the object, the base object that implements a fit method. So personally, I think if my rename that would be fitter, would be much better fit. Anyway, so for the base object in the estimator, they actually fitting the model based on some training data and is capable of inferring some properties on the new data. And the second object named predictor. So the predictor objects implement predict method. Here are some variations in the predictor that called predict probability or decision function. So those are just specific for some classification algorithms. And the third estimator or third core object named model. The non-model objects implement just score method to give a goodness of fit measure or a likelihood of unseen data. All those three, estimator, predictor, and model, they are basically using for the modeling and the learning process. The fourth core object named transformer. Transformer objects implement transform and fit transform methods for filtering or modifying the data. So basically transform for the data using the calculated parameters, apply the transformation to a particular dataset. While fit transform joins the fit and transform method together for transformation of datasets. I found this illustration is very helpful for us to understand the difference between those two, because you can imagine that we only apply the fit on the training data, and then whenever we want to transform our fitted training data, we use fit plus transform, and that's combined to be the fit transform method. While for the transform, we actually only apply for the transform for the testing datasets. So no surprise, together with estimator's fit function for the data without the target, together with the transformers transform or fit transform data, that's actually formed the pretty useful tool for the processing or the feature extraction stage of the work. All those four main objects form the building blocks of model or algorithms we as the end user to use. So in practice, we use or define one class which can implement multiple interfaces or multiple methods together. Say you define a class, and the class can have at the same time have the fit methods, have the predict methods, and have the score methods as well. Having the big picture for those core objects in our mind, then we can dig into the details for different stages to see what Scikit-Learn can provide with us. For example, in data exploration and the data processing stage, Scikit-Learn provides tons of tools for pre-processing, like standardization or mean removal and variance scaling, nonlinear transformation, normalization, encoding categorical features, discretization, and customized transformers. We will give you an example about standard scaler. Standard scaler here meaning standardized features by removing the mean and scaling to unit variance. So you can see that there's a snippet that I copied from the documentations that you can import from sklearn.preprocessing.standard_scalar. And you define a scalar at a scalar, and then you apply the fit transform for the training data. And after the training, you can apply the transform on the testing data. Of course, they have another preprocessing for imputation of missing values that they can import from sklearn.impute. Either by the simple imputer, iterative imputer, KN imputer, or missing indicator, that kind of methods. Scikit-Learn's imputation methods have a slightly difference from the pandas field NA method. In Scikit-Learn impute method, it has to do some fitting first with a couple of more lines, but you can just simply mention mean or median to perform some action. But in the pandas field NA method, you just need to supply the specific values. In this talk, we only review the preprocessing and impute modules in Scikit-Learn. Actually, Scikit-Learn provide other modules in this stage of, stage meaning preprocessing stage of work, such as feature extraction, feature selection, feature hatching, something like that. In the demo session, we will only show the simplest feature extraction method, meaning loading features from dicts. So in the next lecture, the high performance machine learning by Scikit-Learn, we will mention an example using the feature hashing method. There are other specific feature extraction techniques provided from Scikit-Learn, specifically for like text or images, like tokenization, patch extractor, that we don't have enough time to talk about that. Finishing pre-processing the data, so we move to the part that usually to consider to be a core step for a machine learning project, especially when we are doing some research or we want to educate ourselves about the theory of the machine learning. So we may spend a lot of time to study what the model is and how to select the model, and what the loss function is and how to select a loss function, and how can we evaluate the model, how can we training the model. So all those would be a very core part for our machine learning project in a university. As I said in the beginning of this talk, we don't have the time to discuss or to introduce the details for the machine learning models. But I found this diagram that published in the Scikit-Learn official documentation site is pretty useful. They call it the Scikit-Learn algorithm cheat sheet. This is a very rough guide on how to approach problems with regard to which estimators to try on your data. From many standpoints of contemporary machine learning theories, many justification branches in this diagram may not be correct, but I still like this diagram because it provides a very high level of overview, especially to the beginners. For example, you can see that for the Scikit-Learn, they actually solving the 4 area of problems. One is classification problem, the other one is for the regression problems, and then third one is for the clustering problem, and the fourth would be the dimensionality reduction problems. The steps shown up in this diagram still have a lot of practical sense, especially when we are just started for our machine learning project. At the very start, we should check how many samples or data we have. If it is less than 50 samples, we probably need to get more data, to collect more data. If it is more than that, then the next question would be whether we want to predict a category or we want to predict a quantity. If it is category problems, then we should check whether the data has label or has no label of that. If it is the data has label, then we will come into the regime of the classification problem. If it's no label data, then we actually should consider a clustering problem for our project. If the problem is not to predict a category, then we should check whether it's predict a quantity or not. If it is, then we will come into the regime of regression. If it is not neither category nor quantity, then probably we will want to do with some just checking the data to see whether we can reduce the dimensionality of the data. Then we will go to the fourth regime here. So of course, if it's not, then there's some dead end for the tough luck. After identifying which regime we decide to step into, then we are ready to apply our machine learning knowledge to check which specific model that we want to use. For example, in the classification, probably we may need to use SGD classifiers or support vector machines or naive Bayes, that kind of different models for different problems. For the regression problems, probably we first consider about SGD regressors or with other region regression, something like that. I like ensemble regressors. So such and such, we will not detailed to go over the sub branches to doing that, but I think this would be a very good map for us whenever we started to consider about that step in our machine learning project. Luckily, Scikit-Learn provided a very simple and clean code structure for us to use. Specifically, they actually divided the different specific models into different groups, or we should say different modules. For example, like they have the linear model module, or they have a support vector machine module, they have tree module, they have a multi-output ensemble cluster decomposition module. To use any specific model, we just import from Scikit-Learn one of those kind of modules, and then import the specific model name. I just here in this slides I use the example linear model example to showing that in the linear module, so they include a whole bunch of specific models from logistic regression, passive aggressive classifier, perceptron, SGD classifier, lasso CV, or Bayesian ridge. All those kind of models, specific models, are available used by the Scikit-Learn. After identifying the model's name in the Scikit-Learn for your problem, then you can define your model equals to the specific model's name according to this list with a bunch of hyperparameter list. Here, I give you an example for the logistic regressions hyperparameter list. There are a whole bunch of that. You can get the detailed information from their documentation page. Don't worry about that, because in my personal experience, the default hyperparameter values provided from Scikit-Learn are very practical. So you are pretty okay to start it with all those default values, and then you can see how it goes. So after we define the model, and then we can training the model by model.fit for the training data, and then we can use model.predict to using the new data to make the prediction, and then we can use model.score for the new data to make an evaluation for the model. The example that we shown up here, like a logistic regression, is to some extent what we call basic estimators. And there are another type of estimators is actually sort of some higher level of estimators that what we call meta-estimator in Scikit-Learn. And a meta-estimator is a model that actually assembled a group of basic estimators as we shown up here. A simple understanding of what meta-estimator is would be that an meta-estimator accepts not only the hyperparameters in the general sense, but also the base model names in their parameter list. I would say that meta-estimator is a very important part in Scikit-Learn because it provides a large number of classes and tons of functionalities very useful for our users of machine learning. Roughly speaking, meta-estimators can be divided into 5 categories. The first is the ensemble module. It contains all kinds of ensemble methods in machine learning. It uses wisdom of crowd to apply the methods of either averaging or boosting or stacking to combine the predictions of several base estimators for classification, regression, and anomaly detection. As you can show up here, it contains the model of AdaBoost classifier or regressor, gradient boost classifier or regressor, and random forest classifier or regressor. So in our demo, we will use the random forest classifier as an example. Some meta-estimators require a base estimator to be provided in their constructor, like in the multi-class module or multi-output module. Both of them actually implement either multi-class learning algorithms or multi-output learning algorithms to make the regression or classification. All those 3 meta-estimator categories, ensemble, multi-class, and multi-output, those fit a group of classifiers with the same type or similar type on various subsamples of datasets, and they use averaging to improve the predictive accuracy and control overfitting. The subsample size can be controlled with a parameter named max samples. If we set the bootstrap parameter equals to true, that is default. Otherwise, the whole dataset will be used to build each base estimators. The fourth category of meta-estimator is the model selection module. It contains various functions and very useful functions, such as the splitter classes, hyperparameter searching, and cross-validation. As I shown up here, we already showed the example of train test split in our slides, and we will give you an example about the grid search cross-validation or randomized search validation and cross-value score, that kind of thing, as an example in our demo. The fifth category of meta-estimator is the pipeline module. It actually implements various utilities to build a composite estimators as a chain of transforms and estimators. And for example, we will see the examples in our demo about the feature union, that we unite the different features, and the pipeline, and make pipeline, and make union in our demo. So far, we introduced almost every essential step for us to do a machine learning project using Scikit-Learn, at least in a theoretical level. That includes getting the data, acquiring data or collecting the data, and splitting the data into training and testing data sets, exploring or pre-processing the data, and using different models and selecting different loss functions to train and evaluate the different models. I assume they will have a lot of iterations between selecting different models and also iterations between the selecting different splitting data schemes. And ideally, we will get the best model with the highest evaluation score. That will be the one that we want to apply for our new production data to make the realistic predictions for our project. The question that I want to address for The last step of our machine learning project workflow related with Scikit-Learn is the problem of model persistency. In other words, we want to see how can we save and restore a trained model for our project. Actually, there's not much fancy stuff happening in Scikit-Learn for the model persistency problem. User can use Python's built-in serialization, for example, Pico library, to save and restore a trained model. Or because Scikit-Learn have a very good integration with the joblib library, so you can use joblib's dump and load functions to do that purpose. One note is that if you customize your own transformers in the pipeline, it cannot be correctly serialized by the Pico or joblib directly. In that case, you might have to consider to use some third-party modules like a NeuralRack module to save custom pipelines in stepwise. So that's a little bit complicated, but it's can do. Another note for the model persistency is the portability issues you may have. Sometimes the model can be very sensitive for the different versions of Scikit-Learn, NumPy, or SciPy. Sometimes it might be related with your system environmental variables. When you do the Pico process, the serialization and the deserialization process make your model not portable in another environment. In that case, you better to deploy your Pico model using the container techniques. In that words, so everything will be wrapped up in a closed environment so that it can avoid the portability issues completely. There are other solutions for solving the model persistency problem. That is, we can export our model into some common format. I listed two solutions here. One is the ONNX, Open Neural Network Exchange format. So ONNX is a binary serialization of the model. It has been developed to improve the usability of the interoperable representation of data models. It aims to facilitate the conversion of the data models between different machine learning frameworks and to improve their portability on the different computing architectures. I know there are some projects going on, for example, like Scikit-Learn ONNX, so that you can use that to export their ONNX format. Another solution is called predictive model markup language. So we see markup. That means it's actually an implementation of an XML document standard defined to represent data models together with the data used to generate them. Being human and machine readable, PMML is a good option for model validation on different platforms and long-term archiving. So there are some projects going on, and one project that I noticed is Scikit-Learn to PMML, so that you can also try that solution as well. As we mentioned earlier in this talk, Scikit-Learn is not like that kind of a full-fledged framework like PyTorch or TensorFlow. Scikit-Learn is more like a toolbox. It provides standalone tools and you can use that whatever you need it. So I think it would be important for us to know that there are huge number of libraries. It serves as an extension to the Scikit that available for us to use for our machine learning project. For example, there are a lot of libraries that adopts Scikit-Learn's internal code or algorithms to extend the various functionalities. For example, we can read in from different data formats by Scikit-Learn pandas or Scikit-Learn IDRE. We can do the auto ML tasks using auto Scikit-Learn feature tools or NeuralRack. We can do the model visualizations by the D3Vs. We can do the model selections by the Scikit-Learn Optimize or Scikit-Learn Deep. We can export our model into different common formats. For example, like Onyx ML tools or Scikit-Learn to PMML, as we already mentioned that in the previous slides. We can do the parallelization by the skdist. We can also do some additional plotting functions by the scikit-plot. That's all libraries, and there are many, many more that are coming out to adopt Scikit-Learn functionalities. There are other libraries that are not adopting Scikit-Learn's internal code, but they make their design of interface to be fully compatible with the Scikit-Learn ones. For example, if you are doing time series models, you can use TS-Learn or SK-Time or SEG-Learn to have the same Scikit-Learn APIs to do your modeling. And in the deep learning field, the famous one is Keras. I don't know which one comes first, but the Keras have the very similar interface as the Scikit-Learn, and also Scotch. So for other regression and classification problem, the very famous one is XGBoost. So this would be a very famous and very competitive results compared with the random forest models. For the unsupervised learning field, like to do the decomposition or clustering problems, LDA or HDB scan would be a very useful libraries for us to use. Here, I want to say a little bit more words about Scikit. As we mentioned, Scikit is a short term for SciPy toolkits. In Python community, Scikit usually means a bunch of adds-on packages for SciPy. They are hosted and developed separately and independently from the main SciPy distribution. Actually, Scikit is a huge family. When you do the search in Python package index like PyPI with keywords Scikit or Scikit, it can come up with about 2,500 packages. Of course, the most famous one is our Scikit-Learn. And most of the Scikit related packages are just add-ons and extensions based on Scikit-Learn. They form a big Scikit-Learn ecosystem itself, as we shown up in those lists here. But some packages with Scikit are actually unrelated with Scikit-Learn. For example, Scikit-OPT is a good library with a collection of advanced AI algorithms in Python, such as genetic algorithm, particle swarm optimization, simulated annealing, ant colony algorithm, emu algorithm, artificial fish swarm algorithm. And Scikit-Image means a collection of algorithms for image processing. Scikit-Sparse is a companion to the scipy.sparse library for sparse matrix manipulation in Python. And the Scikit-Stats models, so as it says in the name, is a Python package that provides a complement to SciPy for statistical computations, including descriptive statistics and the estimation of statistical models. So feel free to choose any tools needed in the big toolbox. As the last page in our slide section, I want to make these slides as a summarized for the messages that I want to deliver in my talk. So we discussed about learning Scikit-Learn. Learning Scikit-Learn means a couple of things that follows. First is we have to understand the machine learning workflows. There might be different workflows for different projects, but generally speaking, machine learning related with data, modeling, and prediction. And the different steps meaning different tasks, and the different task meaning we have to find different tools in the super good toolbox that provided from the Scikit-Learn. And then we have to learn its API conventions. So basically .fit, .predict, .score, something like that. And the third message that I want to emphasize is that you have to familiarize yourself for its official documentations. As I said, Scikit-Learn documentation is the best in my opinion. It's pretty good. You have to check the documentations by yourself frequently. And also, it's very good for us to inspect or check the example code by ourselves, line by line. So that's a pretty important, maybe the most important step when we want to learn the Scikit-Learn seriously. And also, in some cases, our machine learning task might be related with some functions that the Scikit-Learn itself cannot provide it so far. So we need to consider the Scikit-Learn extensive libraries. Okay, so this is pretty much what I would like to talk about the learning Scikit-Learn basics in slide session. Please stay tuned about our subsequent videos for the demo session for this talk and for our second talk about the high performance machine learning using Scikit-Learn. Thank you very much again, and please let me know if you have any questions or comments. Bye bye.